Write two different equations that describe the relationship between the inputs and the outputs, or in this case, the relationship between A and B. So we want two different equations that when A equals 3, B equals 12, when A equals 5, B equals 14, when A equals 7, B equals 16, and so on. So we want to analyze the values of A and B to come up with a rule to write our equation. So maybe we first recognize that looking at 3 and 12, 4 times 3 equals 12. So maybe we think the rule is that 4 times A equals B. So if we think the rule is 4 times A equals B, which you can also write as 4A equals B, we want to make sure it is true for the other values of A and B. And notice how this doesn't work because when A is 5, 4 times 5 is equal to 20, not 14. When A equals 7, 4 times 7 is 28, not 16. So this equation does not express the relationship between A and B for this table. So looking at it some more, maybe we now recognize that 3 plus 9 is equal to 12. So maybe we think the equation is going to be the value of A plus 9 equals B. Again, we want to test this with the other values of A and B. So when A is 5, 5 plus 9 is 14, so that's correct. When A is 7, 7 plus 9 is 16, that's correct. When A is 9, 9 plus 9 is 18. So we found one correct equation that describes the relationship between A and B. But remember, we need two equations, not just one. So if B is 9 larger than A, then if we start with B, we can get A by subtracting 9. Again, if B is 9 larger than A, then if we start with B, we can get A by subtracting 9. Notice 12 minus 9 is 3, 14 minus 9 is 5, 16 minus 9 is 7, and so on. So a second equation that describes the relationship between A and B would be B minus 9 equals A. So here are two equations that describe the relationship between A and B. Now I also want to mention we could change the order of these equations and write this first equation as B equals A plus 9. And we could also write this equation in the opposite direction as A equals B minus 9. I hope you found this helpful.